Data modeling is the process of creating relationships and rules about objects so that we can decide how to store them in a database. Data modeling defines how we store and query our database systems as well. In today's episode, we discuss data modeling in Cassandra with Jon Haddad, an evangelist at Datastax, the company that works on Cassandra and has Cassandra support. The distributed nature of Cassandra creates some unique rules around how we should model our Cassandra tables. If you are new to Cassandra, there are a few episodes in the past that you may want to listen to before this episode. We did a couple of episodes with Tim Berglund, who is also of Datastax. By the way, I want to thank Caleb Meredith and Ben Johnson from the Software Engineering Daily community who helped the preparation of this episode. And if you want to contribute to Software Engineering Daily and help me prepare for these episodes, you can go to softwareengineeringdaily.com. You can click on the link to collaborate. That's also the road to becoming a host if you want to host some episodes on Software Engineering Daily. And you can also find links to the Slack channel or my Twitter or my email address. I would love to hear from you if you're a listener. I want to know what you are interested in hearing more about or hearing less about. So with that, after a quick message from today's sponsor, we will get to this episode about Cassandra and data modeling. This episode of Software Engineering Daily is sponsored by Braintree Payments. Mobile app development can be complex, but integrating your payments no longer has to be complex. With Braintree, your business can accept nearly every type of payment from any device with just one integration. Learn more at braintreepayments.com/SEDaily. Braintree's API supports Android, iOS, JavaScript, and many other languages. The documentation for Braintree is clear and elegant, and if you're integrating payments into your app for the first time, you can call Braintree's customer service and get assistance with your integration. Don't get frustrated when you're trying to integrate payments and monetization into your app. Go to braintreepayments.com/SEDaily and monetize your app today. braintreepayments.com/SEDaily. Now let's get on with this episode of Software Engineering Daily. Thanks for listening. Jon Haddad is a developer evangelist at Datastax. Jon, welcome to Software Engineering Daily.
Hey, thanks for having me.
Today we're going to talk about Cassandra data modeling, but let's start out by just talking about data modeling in the abstract. What is data modeling?
So basically, you have your kind of business environment. You have a bunch of stuff that you need to store, and you really, I guess you could say that you have two things. You have a bunch of data that you need to store, and then you have the ways that you're going to query it. And they're very tightly coupled. So the way that most people kind of learn data modeling, either in school or if they've used relational databases at work, is they learn this idea of like these normal forms. And that's what most people are kind of familiar with. That's what they come into the world with, but it's really not the only way to do things. Like third normal form is very cool from like a correctness perspective, but it's not always the right way to go if you're building an application that, let's say, is tracking like billions of records with hundreds of millions of users or something. So data modeling can be one of those tricky things, and it's that's kind of the nuts and bolts of it.
And to give a prototypical example that we can use throughout this episode, let's say that we're building a database for a company like Netflix.
Okay.
So we've got movies and users and payments and stuff. What are the different data types that we need to model in our data model?
Sure. Well, if we're coming at this from, let's say, that traditional relational third normal form perspective, those nouns that you just use typically become tables. And a table is something that you can insert data into, and you have records, and you can select from it, and you can put arbitrary predicates and say, I want all the movies that satisfy this criteria. And then you go through this denormalization process where you say, maybe I have multiple movie genres. And so then you end up with a genre table. And then you also have like a table that kind of links movies to genres. But that's not the only way to do it. So if you were to like let's say, come into the Cassandra world, instead of doing this kind of third normal form, let's think about our data first, we actually think about our use cases first. And so in the Cassandra world, the difference is you would say, how do I intend on querying my data? And so you would end up with questions like, or requirements that's maybe, I want to query for all the movies in a particular genre. And so you design your database to be able to answer those questions efficiently. And that starts to matter when you have issues of scale. So the third normal form thing is great, but it doesn't particularly scale well. And so that's kind of where Cassandra fits in.
Okay, so just to underscore that, what are the main differences between how we do data modeling in SQL, like a MySQL database, and Cassandra?
Okay. Well, basically, it starts with, in the relational world, it starts with that third normal form, where we're going to say, I have this data, and this is the way to structure it so that I'm only storing one copy of a particular record or piece of data, and that's some authoritative thing. And in the Cassandra world, the thing that's a little bit hard for people to understand at first, but is really the only practical way to solve the problem, is you end up with multiple copies of your data. So maybe I have movies by genre, and I also have movies by year. And to be as efficient as possible, I'm going to store two different tables in Cassandra. I may say, this is my movies by year table, and this is a movies by genre table. And I have all the information about the movies duplicated into both tables. And the reason why you do that is because when you start to hit, scale, and that's Cassandra is built to solve scale problems. When you have scale issues, it's much more efficient to do one query to fetch data out of Cassandra than to do, let's say, dozens of queries or hundreds of disk seeks. And that sort of thing starts to really matter. So your data model is actually directly linked to your ability to scale, rather than being linked to your data requirements and your purity.
So as we get closer to talking about building a data model explicitly in Cassandra, we should talk a little bit about some of the principles around Cassandra. And in Cassandra, one thing that's important to keep in mind is we don't need to worry about minimizing the number of writes. So this ends up with, we end up with duplicate data, and that's not a problem. So explain why that is. Why is it not a problem to just have as many writes as we want?
Sure. So one thing that's very, very important to kind of, say right off the bat is Cassandra was designed for applications which have very, very high write workloads. And so as a priority, the goal was, let's make it so that when we double the number of machines in our cluster, we double both the read and write performance. And that's not something that you typically get with other databases. So for instance, in our movies application, if we're writing, let's say, 1 million ratings a second, because that's something that a company like Netflix might have to deal with. And all of a sudden, they get more customers and they're becoming more popular. They don't want to have to do major architectural changes in order to, be able to handle all those writes. So what they just, in their case, what they can do is just double the number of machines and they can handle the extra writes. And the way that this works is, so let me back a little bit up before I get into how Cassandra works. In the relational world, whenever you do a write, the database is constantly doing reads. So I might do a write and the database will go, okay, is there a primary key constraint violation? Are there indexes that need to be updated? Are there, XYZ, like a list of things that need to happen? And that's why whenever you add indexes in relational, your performance kind of goes into the toilet, and most of the time people get rid of them as they scale. You don't do that in the Cassandra world. So in the Cassandra world, what happens is whenever you do a write, it just accepts the write, writes it to a commit log, and writes it to an in-memory structure called a mem table, and then it's done. And that's all that happens over the course of the write. So it doesn't even check to see if there's a primary key violation. And so this seems kind of scary at first, but you got to remember the problems Cassandra was meant to solve are ones that are basically, they're usually more like time series problems where you don't have primary key violations because you're just constantly putting in new data that's coming in from sensors, or if it's ratings, then it's okay that you overwrite the old rating. And that's effectively what will happen. An insert can effectively turn into an update. If there is a primary key, we'll call it a violation, but it doesn't actually bark at you. It's not mad. It just overwrites that data.
Got it. So another principle of Cassandra that I want to touch on, and this is related to Cassandra being it's a distributed system out of the box. And one thing you want to keep in mind in Cassandra is that you want to spread your data evenly around the cluster. Why is that important, and why is that going to fit into how we build our data model?
Yep, that's a great question, and that's one of those things that's actually kind of easy to get wrong. And whenever people do it, it really it really makes you have to step back and fix your data model. If let's say you were to take advantage, let's say you were to look at your Cassandra cluster and you were to say, okay, I'm going to do a bad data model. I mean, you may not actively make that decision. You probably won't. But if you did accidentally put a bad data model, maybe you would decide to say, I'm going to use Cassandra as a queue. And Cassandra is a terrible queue. I would never use it as a queue, not as it exists today. It's awful for that. So in a queue, you typically have a list of things, right? Like I put something in the queue, and then later I take that thing out of the queue once it reaches the head. And the problem with that is a queue built with that mindset is effectively limited to a single list of things. And the problem, whenever you have a single list of things or a very few number of things, whenever you're doing reads and writes on them, the way that Cassandra works is that data is always going to live on the same machine or set of machines. So even if you had a 500 node cluster, if you had one queue in Cassandra, you would effectively be talking to one machine, or maybe if you have replication turned on, which you should, it is on by default, you'll have it replicated to 3 machines. So it's kind of like you've got 497 machines that are being wasted. And what you need to do is you need to make sure whenever you're doing your data model, you need to make sure that, if you're doing writes to 3 machines, once you get to 300, you're going to have that same nice distribution of data because it means that you're taking advantage of your cluster. It's a lot more efficient. You don't have 497 machines just wasted. Right.
And listeners who are unfamiliar with Cassandra may be thinking, okay, so I still don't understand why I care about the fact that it's a distributed system. If I'm working in an SQL database, I just need to know that it's got these rows and these columns, and this is how I'm going to access it. They may not have to think so much about the distributed systems component of it, but in Cassandra, it's important to pick a good partition key, and this is baked into how Cassandra works as a distributed system. Can you explain what a partition key is?
Sure, no problem. So within our data model, much like a relational database, we have a primary key, and the primary key uniquely identifies a row. And the partition key is part of the primary key. And a partition key effectively allows us to point to a particular location in our Cassandra cluster, a particular server or set of servers, and we say, okay, the partition key is run through a hashing function, and that determines the servers that data lives on. So if we have, if we picked a simple one like an integer 1, 2, 3, 4, 5, we run that integer through the hashing function. The hashing function generates a hash, which points to a location in the Cassandra. We call it a ring because it's effectively, most people think of it as a circle as a distributed database because it's a shared nothing peer-to-peer system, and those are typically represented as circles. And it points to a location in that ring, and that's where your data lives. And that's one of the reasons why Cassandra is very efficient at reads and writes. There's not this scatter-gather operation. What we do is we typically have a row, and we either know what we're looking for, but we either know what we're writing because we have the partition key, or we know what we need to read, and we have the partition key there. So we can always go to a single server to do our reads. So even if we have let's say 500 node cluster, we don't have to talk to all 500 nodes in order to get a result back.
Okay, so the partition key is the first element of the primary key. So a primary key is composed of multiple things. Could you talk a little bit more about this key part? Like this, explain why picking a good primary key is so important. Maybe you could talk about how we would pick a primary key in the Netflix example.
Sure, that's a great example. So let's suppose we wanted to do something like select. Ratings is a good one because there's a lot of ratings for a given movie, and there's a lot of ratings for a given person. So maybe we would say, I want to be able to select all of the ratings for this movie, right? And I want to know who rated it. Because maybe I am doing something with machine learning. Perhaps, our use case is I want to build a recommendation engine for our movies. And what we do is we would say, okay, our partition key, if we're going to be getting all the all the ratings for a movie, we would say, I want to use the movie ID as my partition key. And then we add in this new thing called a clustering key. And a clustering key lets me put multiple rows inside a partition. So the Cassandra data model has an extra kind of layer inside of it. It's got this partition. So it goes key space, which is basically like a schema or a database in the relational world. And then we have tables, which, is very, very similar to tables in relational. Functionally, they're a little bit different, as I mentioned, but they're the same idea. And then we have the partition. And so we might have a single partition of ratings for a given movie. And all of the ratings will be stored together. And you'll basically have my the user ID and the rating that was in that particular movie. And then on the flip side, you may also have, okay, for a given user, I want to know all the movies that they rated. So in that particular case, you would say the user is my partition key and the movie is my clustering key. And that allows you to group all of the movies that a user rated into a single partition, which again, live on a single server.
Okay, so we've talked through a couple ways to handle these two aspects of Cassandra where we kind of want to we don't need to worry about having lots of writes, and we want to spread the data around evenly. And we also want to read rows from as few partitions as possible. So talk about why this is important. Why is it important to minimize the reading from as few partitions as possible? Because it seems like that could potentially conflict with the desire to spread data around evenly.
Sure. So any given machine is only capable of satisfying a certain number of requests or doing a certain number of operations. And so if you have an option of either doing 1,000 queries all around your cluster and selecting, data from everywhere and having to deal with different network outages, potential network outages, and, extra disk seeks if you're still using spinning, which I hope you're not, or, any of the 500 things that could go wrong. Like in the case of our movies instance, it's really easy to say, you know what, I just want to get a list of all of the ratings and all the users that rated something. So unfortunately, it's one of those things that there's no hard and fast rule. A lot of it is going to come from just understanding your business cases or in your business rules that are around your data. There are cases where you would say it's a lot more efficient to do, let's say, 10 queries than one, because maybe I can't store every permutation and every single query, because if I did, then it would result in me storing 100 or 500 times the data. I mean, there is a point where writes, we don't just say go ahead and do free writes everywhere. It becomes a little absurd, and so it's a bunch of trade-offs. That's really what it is. And distributed systems, every system is about trade-offs, but distributed systems really, really feel it because
yes, we actually had an entire episode called "Distributed Systems Trade-offs" a while ago.
Oh, perfect! Yeah, exactly. It's one of those things that people want to pretend like there aren't trade-offs, and there always are. We can't just have perfect uptime with distributed systems because there are network partitions. And so we have to decide what happens there. Are we down? Are we up? Like, what are we going to do? And it's the same thing with our data model. We either say we're going to store multiple copies and we're going to query it more efficiently, or we're going to do more queries which require more CPU and network but less storage. And those are kind of the knobs that you have to turn and figure out.
Let's talk about building an actual data model. In order to minimize the partition reads, we need to fit the model around our queries. You've said this a number of times. We want to fit the model around the queries. In the Netflix movie database example, what are some queries that we should think about supporting?
Well, I think the first couple that I've mentioned so far, I think are we can start with the basic ones, which was I need to grab lists of movies, right? Or one movie at a time. And then we say, I want to grab movies by genre. I want to grab movies by year. And then, do you want to grab movies by genre and year? Because you would need to you would either need to do multiple queries to satisfy that, or you would need to kind of do some clever data modeling and take up a little bit more space. You also end up with questions like who rated this movie, which is our movies by user table. And then, the who rated this movie in order to do our machine learning. And those you're going to always ask yourself, what are people, like, what do we need to be able to answer? So this problem is definitely a little bit tricky. And the movies one is actually really interesting because that kind of, ties into a side project that I've been working on. And one of the example data models that I'm building out is this exact data model. So I have a project called the Cassandra Dataset Manager. And effectively what it is a way for people to be able to learn Cassandra data modeling by example. Because these types of things, these questions that you're asking right now are the same questions that every single user goes through when they're learning Cassandra.
So how does the project teach different ways to build that model?
So the goal of the project is to I'm going to jump out on a limb here and assume that you've heard of apt or yum. And
safe assumption.
And basically, yeah, it's reasonable. Well, those tools allow you to easily install applications. And so what I realized, and what we kind of, Patrick McFadden, who's the chief evangelist over at Datastax, we've talked for years now about how cool it would be is if you could just install data into your Cassandra cluster for the purposes of learning. And that's effectively what the Cassandra Dataset Manager, I'll just call it CDM, that's what CDM is for. So you would type CDM install movie lens, and it goes out and it grabs it, and it just grabs the data and installs it into your Cassandra cluster. And so if the first thing that you do after you download Cassandra is ask yourself, like, okay, now what? This is probably the right answer. And so along with each data set, you can effectively take a look at a bunch of resources that are available. Like there might be blog posts, and there might be Jupyter notebooks, and there might be Zeppelin notebooks. Or I think, there's just a million things that we can build around established data sets that make it really easy to teach things. And then that way, the people that understand the data model can build really, really good data models and kind of explain how they work. And then people can build interesting stuff on top of it. Spark notebooks were the last one that I was thinking of. So you can effectively start with a bunch of canned data models that are done, in a way that will scale really well, and then build a bunch of content around it so that people can learn how to use this database, because it is a little bit tricky, but the reward is absolutely massive.
So what are some more complex queries that we might want to be asking on this data set that would not be answerable in the ways that you've explained so far, where we'd have to do something more fancy?
So Yep, and that's a really good question. So I touched a little bit on the machine learning. If you were to, let's say, want to look at your entire data set and generate recommendations for every user based on every movie that they've ever rated, that's a really good example, because if you've got if you've got a 50, 100, 500 node cluster and you're going to go, okay, I need to do analysis of this, it's a lot harder than, let's say, in the relational world, where maybe you could pull everything out and just do it in memory and who cares. But fortunately, so let me back up a sec. Effectively, what we have, the problems that Cassandra doesn't solve very well are ones that are more on the analytics side. Let's get the average rating of every movie in the database based on all the ratings. Let's get the genre breakdown, or do some top K type query leaderboards. Those are definitely not Cassandra's historical strength, and that's okay, because fortunately, we've got a ton of really good open source software, especially in the Apache Foundation. Tools like Spark, which have gotten ludicrously popular over the last few years, have been very, very helpful in complementing other tools like Cassandra. And fortunately, Spark works very well with Cassandra. So the things that we don't solve particularly well in the Cassandra world, we usually can look to Spark and say, well, you've got an analytics problem there. This will complement your database, very nicely.
And you've given a good talk on that, which I saw on YouTube when I was preparing for a previous interview I did with Tim Berglund about Spark and Cassandra. But talking about a simpler query that we might be wanting to make on a table in Cassandra, let's say we want to create the ability to query our movies by category. So comedy or drama or action movie. How do I make a table that, well, first of all, am I going to have to make a new table in order to have this query, and how would I make that table?
Sure. So that's a great example, because there are a number of there's a finite number of categories that we're going to have. Like, we're not just adding new genres, right? It's just, there's a list and whatever. And the reason why that question is so tricky is because it's going to affect your partitions and the way that your data is spread around. So if you were to have the tricky part about this kind of ties back to a question that that you brought up earlier, which was, how does the partitioning affect your cluster? And so if you were to pick genre or category as a partition and you only have 50 categories, well, then you might run into a problem, because you're going to have these really, really heavy partitions. They're going to have most of the movies in them. And the movie database is obviously an example, and we can fit that in memory on my laptop, and that's not a problem. But, in the real world, when we've got these humongous data sets, and all of a sudden now we go, hey, I have 1 billion items in this one partition, that's not going to work very well. And so what you do there is you typically figure out another way to partition your data into smaller sections. So maybe in the movies example, you would say, I'll break it down by year, and I'll have one partition for each genre and year. So I can look and go, okay, I want to get the, everything from the 80s that was in comedy. Or maybe I partition by, the first whatever n number of letters. So if I'm anticipating lots of data in there, maybe I'll say, I'll just start with the first 3 letters. And the reason why that's cool is you can quickly jump to any section in your list of movies, and it becomes a lot easier to manage.
So let's say instead of movies, I'm indexing TV shows, and I wanted to index TV show episodes, and I wanted to add a notion of time to my data model so I can know how recently an episode came out. How should I add the notion of time to my data model?
Sure. So if we were to do I think the most straightforward way to do this is you have a partition for each TV show, and then we come back to our clustering column, and that's where we have our notion of time. So if we were to use, let's say, date as like date aired or date time it was aired. We effectively now have TV shows expressed as time series. So if you think of that, if you think about your TV shows expressed as a list with the ordering of the list going by time, and we're only appending to the end of the list whenever we get a new TV show, that's effectively what we get when we have a clustering column that's done by date time. And that's how you would accomplish that.
As an engineer, you want to minimize scalability issues. When there is high traffic to your application, you need your content delivered with 100% availability. CacheFly is the content delivery network with the fastest global throughput. Every application needs a CDN, whether you are in gaming or ad tech or social networking or e-commerce. If you're at scale, you need a CDN. Go to cachefly.com. That's CACHEFLY.com and use promo code SEDaily for a 14-day, 2 terabyte free trial. 65% of CacheFly customers use CacheFly for software distribution because CacheFly has the fastest throughput globally for large files. Try out CacheFly for free today. There's a 14-day free trial up to 2 terabytes of bandwidth. And if you use promo code SEDaily, you can help support Software Engineering Daily. If you want your app to be successful, you can't have delays and downtime. So check out CacheFly, CACHEFLY.com, and use promo code SEDaily for a discount. It would support the show. Now let's get on with the show. And thanks to CacheFly for being the newest sponsor of Software Engineering Daily. So now that we're on the notion of time, Cassandra is widely used as a time series database, and you mentioned that earlier. Mm-hmm. Why is that?
So time series is very, it can be very tricky. And the big problem with time series is that it's typically very, very write-heavy workloads. And so it's that's where other databases kind of struggle, is when you say I've got 99% writes and maybe I've got 1 million writes a second happening and they're just happening forever. That's one of those problems that becomes very expensive to solve if you're looking, towards, let's say, Oracle. It becomes ludicrously expensive because now you're putting everything on a SAN. And you've got, tons of extra stuff that you have to buy in order to make it work. And, it ultimately it does fall apart. Cassandra does really well here because as I mentioned before, a little like kind of in passing, Cassandra is built so that as you double the number of machines, you double your throughput. So if I'm doing time series, a big use case is like sensor data. Okay, so let's say I have my weather station data, and that's just coming in, or maybe I have like some data recording, earthquake, seismic activity, and I want to get more accurate with that. Now I have double the number of sensors out there, and so I've got double the number of readings coming in, and that's one of those things that's really, really tricky, because if you haven't planned for that, if you didn't, get a bigger SAN or whatever, it can become a huge problem. But fortunately, in the Cassandra world, we're doing everything around commodity hardware. So you would just double the size of your cluster, and what do you know? You can handle twice as much time series, both from a disk perspective and from a write perspective. And that's really why people use it, is because generally people don't write less data; they just keep writing more.
So if we were collecting temperature data, for example, let's say we're in a warehouse and throughout the warehouse we have 10 internet-connected thermometers, what are some different tables that we would need to create to store this temperature data? How would we create a data model for this type of application? And are we going to need to write a time series for each of those 10 thermometers on every database that we want? I mean, it seems like that data could grow out of control really quickly.
Yep, and it definitely can. So one of the things that people do that's pretty common is you have one, maybe you have one partition for each sensor reading, right? But as you know, as you're kind of alluding to, there's that information by itself isn't particularly useful. So usually what happens is you end up aggregating it up multiple levels, and you may say, okay, like, you know, I have my sensor data for weather stations, but one weather station's sensor data is generally useless. Like the sensor may be broken, or, you know, it only gives you that particular location. And so what you would end up doing is storing multiple copies where maybe you'd say, oh, I have my California sensor data or my Seattle sensor data. And you may aggregate into a thing there, or you may partition by day. And then that way I can say, what was all the sensor readings for this particular day? And that's very efficient. And then the other thing you can do, which you kind of, you brought up there, that data can get out of control. And so one of the things that Cassandra is also really awesome at, and this is like, you know, for a lot of people, this is like the killer feature, is you can TTL your data on insert. So I can insert data and go, you know what, like after a week or after a month, I don't even care about the raw data because I've sliced and diced it 100 different ways and like gotten everything I need out of it. Just get rid of it. And there's not like a job, like a cron or something that you have to run in the background to to purge it for you or do anything like that. It's just part of the normal Cassandra process that it will purge your TTL data for you. And so that's how you avoid getting out of control.
So if I wanted to store time series data from a rolling 10-minute window or a weekly window and then constantly garbage collect the rest, are you saying that the best strategy for that is to put a TTL on every entry?
Effectively, yeah. So you'd put a TTL on the entries. So if you were to, you know, if you wanted only the last week's worth of data, whenever you put your data in, you just TTL it for a week, and Cassandra takes care of the rest.
And the TTL stands for time to live for listeners who don't know. So what if I didn't want to throw away any of the time series data? I want to store it though. And is there a way Cassandra can compress it? Is there a built-in ability for that?
So basically, out of the box, your solutions are effectively to just let it sit there. You could there are some tricks that you can do. Like you could create a table for each month. Let's say. So I'll say I have my July data, and I write to my July data, and then August comes up, and I go, okay, I don't need my July data. I can effectively take a snapshot of that table, and you could put it somewhere else. But Cassandra doesn't have a means of, say, I want to archive this table as a read-only thing. It would be very cool if it did, if someone wants to write that. But right now, that doesn't exist. So typically, what I recommend people do is, this is where Spark comes in handy. It's nice to be able to just say, okay, I'm going to take this table and archive it in Parquet form. And you put it on just some HDFS file system. You can either put it in HDFS itself or S3, or Microsoft's cloud has their thing, their file block store, I think it's called. It's and you end up getting like crazy compression, because that's really one of the things that Parquet is great at, and it also ends up being faster to query. So you end up with a really cool means of archiving old data and also making it faster to work on.
Okay, so we've talked about some more reductive examples. I kind of wanted to have a more advanced discussion. So I don't know if I'm sure you have some insight on this, but let's say I'm working at Facebook, which is where Cassandra was originally developed, and I think when Cassandra was developed, Facebook basically had a bunch of MySQL tables, or maybe you have some more insight on that. But how would you make a migration like that? How would you I mean, we could talk about Facebook, or you could talk about some broader extrapolable example of migrating MySQL to Cassandra. But this is sort of like the data model transposition, perhaps. How would you orchestrate that migration?
Yep. So as far as Facebook goes, I don't know what their Cassandra usage is right now. I know they purchase Instagram, and Instagram is a big time Cassandra user. Outside of that, I'm really not sure. So I think it'll have to be a little bit more vague. But so let me back up a sec. So one of the reasons I know Cassandra is because I did several of those migrations. And I migrated away from a combination of MongoDB and Neo4j to go into Cassandra. And the thing that I've learned in like the 15 years of programming that I've been doing professionally is to like try and nibble at these problems. And this is something that's it's so hard to like have self-control when it comes to doing a database migration, because most people are like, we're going to rewrite everything and it's going to be amazing. And I've tried to do that before, and it never goes well. And so if you're going to, move out of the relational world, or you're going to move away from Mongo or Neo, whatever it happens to be, and you're going into a system that you've never touched before, the most important thing that you do is that you learn this new system. And the only way to do that is with production usage. But it's not like just throwing everything into production and hope that it works, because, odds are you probably didn't get the data model 100% right in at least one of your use cases. So what I advise people do when they're going to migrate from another database to Cassandra is to pick something kind of small, and they prototype, and you put it in prod, and you see how it works, and you get used to monitoring and backups, and what's the impact of a TTL, and what's a tombstone? I mean, there's a whole bunch of questions that sort of just like come up, and then you learn about the system, and you move towards bigger and bigger projects, and that's really the way to go.
Well, this is very similar to the discussion around migrating to microservices from a monolith, where everybody who has come on the show has said if you want to make that migration, you start with some small non-production impact service, split it out from the monolith, and then start feeding traffic to it. If everything goes hunky-dory, then you start migrating other more production important components of your monolith to microservices. And this is philosophically the same idea, where you start to move parts of your data model to Cassandra. Maybe this is too far flung, but does GraphQL fit into this conversation? GraphQL is this server intermediary between users on the front end who are requesting data and heterogeneity of databases that may be underlying that server. We've had a couple episodes about GraphQL and Falcor. Does that fit into this conversation?
So it could, and it could definitely make that process easier. So I'm also a big fan of microservices, and everything that you just said philosophically is exactly the same. And I think in general, whenever you're trying to make changes, it makes sense to do things a little bit at a time and keep things stable, rather than try and pull the tablecloth off the table and just hope everything is okay. It makes things a lot easier from an operational perspective and from a developer perspective to work on these things incrementally. Having something like Falcor and GraphQL in front of it is one of those steps that will make that process in your life a lot simpler, because if you're requesting something, like if I'm a mobile developer and I'm requesting something, it's nice that I don't really have to care what you're doing on the back end. And it's one of those tools that helps kind of, make the back end a little bit more of a black box. And I've definitely worked on some projects where people intentionally expose what's happening on the back end. And it's very obvious that you're using one particular type of database or another. Like maybe you pass a fragment of a SQL query into the back end in order to ask for something. And, that's just a bad engineering design for a number of reasons. Exposing what you're doing on the back end is definitely going to make it harder to make changes there. Not to mention, the security risks associated with just whatever. Give me any data the front end wants.
That makes a lot of sense. Okay, but so getting back to the migration question, I kind of deviated you there a bit. You mentioned this MongoDB Neo4j database you had that you migrated to Cassandra, so you have some experience with this. I don't know, maybe you want to talk about that or some other migration, and I'd just love to hear about some more of the, up close issues about what are the changes you need to make to the data model to perform that type of migration?
Yeah, so I'd love to talk about that because it's one of those things that has there's some hidden costs, and you may not be aware of them when you make them, unfortunately. So the interesting part about this migration, about moving away from Neo and moving away from Graph in general, is you find that when you use something like a graph, you end up with, or relational for that matter, you typically end up with this really, really tightly coupled backend. And that's one of the challenges of moving away from, either monolithic services or moving away from something like a graph or relational in general. Because what happens is you end up having all of your data kind of interconnected and all these like tight couplings and these interdependencies. And that's really, I think, the pain of moving towards either microservices or changing databases. Like even if you had a monolith Cassandra like deployment, you still have to move everything out of relational or graph and go there, or Mongo and go there. Mongo is not as hard because there's no joins, so you're okay there, and that wasn't a big deal for us. But moving away from a graph is inherently very difficult because you're breaking these connections that you spent so much time building, and there can just be a lot of dependencies there. So one of the reasons that the cautionary tale for me is if you're going to use a graph database, just kind of be aware of the potential problems from migrations or from just changing your data model, and that can be a little bit tricky. And the same advice goes with relational.
So when you were moving from Mongo or the graph database, were the relationships among the data, did they no longer fit the graph representation of your data? What exactly was the motivation or the...
So our data model was actually a pretty terrible data model to use a graph database on. It's just that the name of the company I was at happened to have graph in in its name, that someone decided to use a graph database. I wish I was joking about this, that I fought this, but yeah, it was one of those ridiculous decisions that really didn't make any sense. So we just had a bad model for graph. So effectively what we had is we made the trade-off of none of the advantages of graph with all of the trade-offs in the other way. And if you're going to use a graph, I actually love graphs. I think they're really, really cool. But for us, it was just totally the wrong choice. So migrating out of it was really easy because we just had lists of things. It was like, give me a list of all the users on this message. Okay, well, as we talked about already, that's a trivial Cassandra query. That's an easy data model. But asking the graph, give me all of the people, like how do I know you? Let's say we had never met and I asked the graph, how do I know you? And just find a path or find all the paths in 4 degrees of separation. Well, the graph can answer that, which is really cool, but we weren't doing any of that. So yeah. So without that, it's a waste.
What's the most challenging data schema that you've ever modeled?
Let me think about that for a second. I did some really kind of tricky stuff with a large. So this was before my Cassandra days. I had a 7-level taxonomy that I worked on for a project. It's still up, but none of my original code is there, I'm sure. For answerbag.com, and Answerbag was like a Q&A site that was similar to Yahoo Answers, and we were relatively close in size at the time. And there were some tricky things that we had to do, like to be able to look at any top-level category and see all of the questions in all of its subcategories and like sort it by rating and filter by a handful of different things. And it was just relatively tricky because, we were on slow spinning disks. So for us, like minimizing the disk seeks was a big deal because you're effectively, for every seek you're paying, at a minimum of 5, but more realistically, like 10 milliseconds. And, you got to get your data model like perfect there, especially when you're dealing with tens of thousands or hundreds of thousands of requests per second that could come in. So you kind of have to get really, really like creative with your caching, and you actually start to design your relational data models in the same way that you design Cassandra data models. That was actually one of the reasons why Cassandra data modeling made so much sense to me, is because I had jumped through enormous hoops to fix relational data models that weren't scaling, and I start designing all these tables to answer specific queries, but then I've got like still all the overhead and all the trade-offs of a relational. Like it doesn't really cluster at all. There's a whole handful of things that you trade off, and I really didn't see any of the benefits. And so when I started looking at Cassandra, I was like, oh, so these exact data models that I built over here in the relational world to scale will work. Plus I get all the distributed awesomeness and like the fault tolerance. So that was kind of like, that was my like life journey from the relational world into the world of distributed systems.
Nice.
Yeah.
Okay, so I've got a couple listener questions to wrap up with. One is, how does client-side caching affect data modeling?
So that's a good question. And like any reasonably good question, the answer is, of course, it depends, which I hate, but it always is that way. So the tricky part about client-side caching is it depends on what you're caching. So if I'm doing something like I'm caching one row, and I'm or not, maybe not one row, but I'm caching individual rows, well, in that case, it may not be worth it to actually do caching. And so it's like, okay, I can cache one row, or I can go to the database and cache one row, but my database just kind of scales for me anyway. So what's the point of caching? Like usually you put caching in front of relational databases because sharding relational databases is hard. So let's just put caching in front as a band-aid. And you typically don't really need that band-aid. So in the systems that I've built with Cassandra, I've skipped caching altogether, and I just go straight to the database, and I have more efficient data models. But there are times where maybe you're like, I want to cache some like hard to compute thing. Like, I've got some admin panel, and maybe I can ask, maybe I don't know all the questions that the user is going to ask, but I do allow them massive flexibility. And so maybe it takes 30 seconds to compute something, and I just say, okay, I'm going to cache that. And I just deal with the fact that maybe my cache is stale sometimes. And that's where you end up. But like, I think, I have to keep mentioning this, because since Cassandra is a database that's optimized for writes, there's very few cases in like IoT where you're going to cache your data, because if you need to bust that cache as soon as it's changed, like if I go, well, I want to cache my, the last 10 seconds of data, well, if you get a stale cache read, it doesn't really help you out at all. So I think a lot of what happens is for high write volume stuff, people kind of drop the caching. And if you're using Cassandra for more of the high availability side of things rather than like its scalability attributes, then maybe you'd put some cache in front of it in order to make it a little bit faster, but you're not going to gain a ton by doing that.
Interesting. That's a very interesting question. Well, Jon, thanks for coming on the show. This has been an awesome conversation. It was really a pleasure meeting you at, where did we meet? OSCON?
OSCON, yeah, it was OSCON. Yeah.
Good to meet you. And I appreciate you coming on the show. I love doing these shows on Cassandra.
Yeah, thanks a lot. I really appreciate it. It's been really cool talking to you.
Thanks to Symfano for sponsoring Software Engineering Daily. Symfano is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symfano.com/sedaily. That's symphono.com/sedaily. Thanks again, Symfano.
Wow.